say we have a set 1, 3, 5, 10, 11. So this is a set with five numbers, right? So what will be a valid subset? So valid subset. So we call the original one a set, and we can say this is set A, right? Set means a collection. Yeah. And A is the name of this set. Yeah. So valid subset of A, right? Of A. It can be like one, right? Just one numbers. So a subset just means you pick any numbers from this original set. But you cannot pick repeatedly. Meaning like if there's a five here, right? You cannot pick it like two times. You can only pick it one time or zero time, right? Or a valid subset is one, five. Or you can. It's also valid to pick them all, right? So these are all valid subset. And also there is another extreme case where you can pick nothing at all. This is also a valid subset. Yeah. And this is also a valid subset. But in this case, we require it to be non-empty, right? We require it to be non-empty. So this is what we called an empty subset. Yeah. So let me put it into another line. So this is called an empty subset. And we need to exclude this. So that is why we minus one here. Yeah. So now I want each of you to give me another valid subset of this set A that I have not written here. Yeah. So Hector, can you give us another valid subset?
Uh, 1, 3.
Exactly. Yeah. Let's pick one, three. Maybe MIU, can you give another subset?
I'm so confused. 110? I don't know.
Yeah, 110. Yeah, yeah, it's right. So you can pick any numbers, and as long as each number appears at most one, right? It can not appear at all, just like this empty subset, right? So no numbers appear, and you can let any of them appear, but for each number it can appear at most once, then it's valid. Yeah. And Jason Huang, can you give another subset?
Um, 11.
11. Cool. Yeah. So that is a single number subset. That's also valid. And Mark, can you give us a subset with four numbers?
3, 5, 10, 11.
Exactly. You see, now all of you have understand the concept of what is a set and what is a subset, right? Subset is just a part of the whole set. Yeah. So if you think the set as a class, right? So a class contains a lot of students, right? Then a subset is like a team, right? It's a team out of the class. So a class may have 30 students, and a team may only contain 10 students out of that 30 students, right? Or even five students out of the 30 students, or maybe two students can form a team. So two students out of the 30 students, or in some cases, the whole class form a team. So 30 students form a team, right? So you can think of set, the original set, as a class, and subset as a team. And there's no restriction on the team. The team can have all the students or can have no students at all, right? But in most cases, we will exclude the empty subset. So when we count the number of subset, we always count non-empty subset. So as you can understand, we don't want a team with like a zero students, right? One student is also valid for a team. Maybe the student is very strong and he wants to do all the project by himself. Yeah. So so here is the definition of subset. And can anyone guess a number like so excluding this empty subset or let's actually include it. So make this also count, right? So empty subset also count. Then how many subset, how many different valid subset are there for set A? You see, these are all valid subsets, right? So what is the total number? I mean, there are also tons of subsets that we haven't written yet, right? Like 3, 5, 10, like 3, 5, 11, 1, 3, 5, 1, 3, 10, 1, 3, 11. pretty much, right? A lot of them exist. So what's the total number? Let us, so I will give you like 2 minutes to think. I mean, like seeing this, you probably can already guess the number from this, right? We have 30 numbers and then it's 2 to the 30. And then, so how many subsets are there if we only have 5 numbers? Sort of already give you the answer, right? But even if you know the answer, you can guess the answer. So I will give it to you each of you 2 minutes to solve this problem. So if you can guess the answer, good. That is really good. If you are on AMC exam, you get the correct answer, then you get the points. But I really want you to really think the logic behind, right? So why is it so why 30 number a 30 number set has 2 to the power of 30 numbers of different subset? Yeah. And then why is the answer you guess, right? So you may guess a number and you think the reason behind. I give you 10 minutes, 2 minutes, 2 minutes. Yeah. And after 2 minutes, I will, yeah, I will randomly ask a student to explain. Yeah. Okay. So let's get back. And Hector, have you got an answer for this? The number of subsets, different subset of A. It has 5 numbers, right? Any guess on number? Maybe MIU, can you give a number and any guess?
With non-empty subsets, is
Yeah,
it
but it's not empty
31?
subset. Yeah. So what's the answer?
31?
Actually, with a non-empty subset, it's 32. So you actually have a correct answer. So it's 2 to the power of 5, right?
Mm-hmm.
I mean, excluding the empty subset, it is 31. And if we include
Yeah.
the empty subset, it's 32, 2 to the power of 5. And can,
Mm-hmm.
do you know the reason behind?
Because it's 2 to the power of 5 because we have 5 numbers, and it's
Yeah,
if it without the empty subset we minus 1.
yeah. But why is it 2 to the power of 5? So why 5 number has 2 to the power of 5 different subset?
Uh,
I mean, you're really clever that you find the patterns, right? But why?
I'm not sure why it's 2.
Okay, maybe Mark. Mark, do you know why it's 2 to the power of 5 different number of subsets?
I don't know. I'm not sure.
Okay, actually, let me give you a pointer or hint. Actually, it's pretty simple. So you can think how the subset is formed, right? Subset is formed by picking numbers from A, right? So we can either pick one or not pick one, right? So so you think of this process. We have 5 students in the class, and we try to select a team, right? Select a team from the class, right? From the class. Okay, so what is the process? For student one, right? For this one, student named one, we can either select one or not select one, right? So we have two choices. For this student, the student whose name is 3, we can either select him or not select him into our team, right? So if we select him into our team, it's one possible way to form a team. If we don't select him, it's another possible way, right? So we have two choices. And for 5, we also have two choices, right? For 10, we also have two choices to select him or not select him. And for 11, we also have two choices, right? So this includes every subset. Also include the empty subset. Because why? Because if we do not select 1, and we do not select 3, and we do not select 5, and we do not select 10, and we do not select 11, then we get an empty subset. And if we do select 1 and select 2, 3, select 5, select 10, select 11, we get a subset or get a team with a whole class, right? So it's just that simple. 5 numbers. For each number, we have two choices to either select him or not select him, right? See this 1, 5, we select 1, now select 3, select 5, now select 10, now select 11. And for this, we select everything. And for this, select 1, select 3, not select 5, not select 10, not select 11. See? So for every number, you have only two choices to either select him to include in the subset or not select him to exclude it from your subset, right? So then 2 to the power of 5 get the whole numbers of different subsets, right? So now maybe like I'm not sure. Yeah, I'm not sure. So now can you briefly explain why there are to the power of 30 minus 1 distinct non-empty subset out of this set of 30 numbers, 33-digit numbers? Yeah,
Because every like every number you can either select it or not. So because there are 13 numbers, so there would be
so you have 2 to the 30.
like I don't know what to do with the -1.
Yeah, so why do we minus 1? So maybe Mark, can you answer why we minus 1 here?
Because we don't include the empty subset.
Exactly, because so this is the number of non-empty subsets, right? So, I mean, if either each number you either select him or not select him, then you may get a situation when you do not select any number. So then you get an empty subset, right? So like for each student, you can select or not select. And then there's a case when you don't select any students. And in that case, your team gets 0 students. We call that an empty subset. And we want to exclude the empty subset because we want to count the number of non-empty subsets. So that's why we minus 1 here. See? Now all of you knows how to count the number of subsets. So now we in just 10 minutes or in just 15 minutes we achieve two things. One is that all of you get the concept of a set and what is a subset, right? So now you are familiar with this concept. This is a very important mathematical concept. And now you also learn how to count the number of distinct subset and also the number of distinct non-empty subset. Yeah, cool. So since like we have 30 numbers and we count the number of subsets and we found that there are 2 to the power of 30 minus 1 distinct non-empty subset, right? So by a subset it means just sum of the numbers like from a team. How many ways are there? There are 2 to the power of 30 minus 1, which is actually quite large, right? You see, so this does not mean 2 to the power of 30 minus 1 equals 10 to the 9. It means that it's approximately equal. And actually, you could even find how equal it is. So let me find a calculator. So actually 我分办法。So 2 to the power of 30 minus 1. Okay, so the answer is this. So you say is like a 10, it's actually a little bit larger than 10 to the power of 9, right? So it is 1 and have a, so it has 10 digit, you see 10 digit here. So it's slightly larger than 10 to the power of 9. Yeah, but very close. So it means, so this means approximately. Yeah. So, and we know that 10 to the 9 is larger than this number, right? So then another question. So since these are 7-digit numbers, right? So each 7-digit numbers must be from between 0 to 10 to the 7. And why is this? Hector, do you know why? So each 7-digit number is between this.
The largest, wait, yeah, because we can have 7 0
Yeah.
and it's 0, and we have 7 9s, then it's like approximately equal to 10 to the power of 7.
Yeah, exactly. And another question. So why is the sum of so we have a 37-digit number, right? Why is their sum at most days?
Uh, hmm?
So why is the sum of 37-digit number at most this number? I mean, each 7-digit number is between days, right? So why is the sum at
Yeah.
most days? So why? Why is the sum of all 7-digit number at most days?
Because if we have 30, the largest
Yeah,
30 of the largest 7-digit number, it's yeah.
exactly. Yeah. So if we have a 37-digit, and so since each one of them should not exceed this, right? So 30 times this is 3 times 10 to the power of 8, right? And of course, 3 times 10 to the power of 8 is less than this. So what does that mean? So that means that you pick a subset, right? A subset may have a sum, right? So you have 30 numbers. Say you pick 5 numbers, and you can sum it up, right? The sum is at most this, right? And you pick 10 numbers, and 10 7-digit number, you sum it up. It is also at most this. And you can pick like 11, 12, or 15 numbers. So 15 numbers out of these 30 numbers also form a subset, right? So you can pick any subset. Each subset contains at most 30 numbers, and the 30 numbers, when you sum it up, since it is all 7-digit number, so you cannot exceed this, right? So each subset will corresponding to a sum, right? So say your subset has 5 numbers, we sum it up, then that is called the sum of that subset, right? So each subset has a sum. And but since each sum is no more than this, right? But how many sum do we have? Because we have this number of subset, so we will have at least this number of sums, right? So everybody get this because we have a lot of subset, and each subset we can sum all the number in the subset, and we get a sum, right? So we have these numbers of sums, but the value of our sums is at most this, right? Because the value of the sum must be between 0 to this. So then the values of sum, the number of values of sum, right? So the number of different value of sums are holes, and our number of subset is pigeons. So 2 pigeons must be inside one hole. What does that mean? That means 2 subset. So there exist at least 2 subsets that has a same sum, right? Yeah, I know it's a quite a convoluted thought. Maybe Emma, can you briefly summarize or explain why 2 subsets must have a same sum? Yeah,
I don't really understand.
you don't really understand. Okay, so let's follow this step by step. So say like say you have 30 numbers, right? 30 numbers. Okay, so and step one. So how many subsets are there? So Amma, you can answer this question. So how many subsets are there from the 30 numbers? Not non-empty subset.
Uh, 2 to the power of 30 minus 1.
Yeah. And 2 to the power of 30 minus 1, we can say it's something like 10 to the 9, right? It is a large number. Say it just equals 10 to the 9. Okay. So there are quite a large number of subsets there, right? And for each subset, it can have it has a sum, right? So what does it mean by having a sum? Say subset one, say 1 1 1 1 1 1 7 digit. Let it be 0 0 0 1 1 2 3 0 0 0 0 0 5 0 and 2 3, and maybe like a 1 0 0 0 1 9 8 8. Yeah. So say this is a subset, and this subset has a sum. So what does sum mean? It means this plus this plus this. So it has a sum, right? So each subset has a sum. So Emma, you can use, answer the question that what is the range, right? A range of the sum for each subset. Range of the sum. So it must be greater than zero, right? It must be at least zero, right?
Mhm.
Actually greater than zero. So it must be less than what? Remember, it's 7 digits.
Mm.
So 7 digits is less than 10 to
10
the
to the
power
power of 7?
10 to the power of 7. Yeah. But each number is less than 10 to the power of 7. And we how many numbers can we have at most? Remember that we are a subset of 30 numbers.
3 times.
Yeah, so times 30, right? Because each
Mhm.
number is less than this, and we have at most 30 number. Because we are a subset, and we may have only 3 numbers or 5 numbers, right? But at most we can have 30 numbers. Do you agree on this?
Yeah.
Yeah, so then what is the range of the sum of our subset? So it's something from 0 until 3 times 10 to the power of 8, right? You agree on this? Yeah.
Mhm.
Okay. So we have this different number of sums. But how many subsets do we have? We have 10 to the 9, right? We have a lot of subsets. So what does that mean? That means two subsets must have the same sum. Do you agree on this? It's like,
Mhm.
for example, it's like you have 5 subsets, right? And each subset you can take on value either 1, 2, 3, right? Say then one subset may take a value of 1, and the other 2, another subset is 3, and then another subset it can be either 1 or 2 or 3. Then it collide. So two subsets have the same sum, right? Do you get this?
Mhm.
Yeah. So we have 10 to the 9 subsets, but each subset can only take a value of from 0 to 3 times 10 to the power of 8, which is less than 10 to the 9, right? Do you agree on this? Yeah.
Yeah.
So now do you know why we can confirm that there must exist two subsets that have the equal sum?
Yeah.
Yeah. So now you get it. Yeah. So what does it mean by two subsets having the equal sum? Say the original 30 number, right? Let them be x1, x2, dot 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 x30, right? So this is the original 30 numbers. And say we have x1 plus x. So say one subset is x1, x2, x3, and x9 and x11. And this subset has the equal sum with say x1, x4, x9, x12, x20, x29, right? So what does this mean? This means you sum this together, right? So this is a subset, and this is also a subset, right? So this means that you sum them together. You sum them together. And what do you get? You get this sum equals to this sum. And of course, like with two different subsets, they may contain the same number, right? So like two team may contain like contain duplicated the student, right? So student like a student one is in team one and is also in team two. So this may be possible. We can only show that the two subsets have the same sum, but this two subset may contain like repeated like number, right? Out of these 30 numbers. Yeah. But we don't need to worry about that. Why? Because if they contain the same number, we can just minus this number from both sides, right? Say they both contain x1. So plus x1, they are all equal. Then if we both minus x1, they are still all equal. They both contain x9, and we minus x9, they are still all equal, right? So we get the case here. So x1 deducted or minused from both sides, and x9 minus from both sides. So see, Now, as long as they have the same number, right? As long as one number repeated on both subsets, we just remove it, and the total sum won't change because we remove the same stuff. Then eventually we will get some numbers sum together equal to other number sum together, and they don't have a repeat number, right? So what do we eventually get? We get that um, there are two disjoint subsets. So what does two disjoint subsets mean? Disjoint subsets means that two teams do not have overlapped students, right? So no student appears in both teams, no number appears in both subsets. Then we call this subset disjoint. So they don't intersect, they don't overlap. Yeah. So this means that if given any 37-digit numbers, right? Given any 37-digit numbers, you can always find some numbers, some group of numbers, and another group of numbers. And these two group don't have like a repeated numbers, and their sum are equal. So this is our finding. So you don't need to say like this specific 30 numbers. It's like any 30 numbers, as long as they are 7-digit. You can always find like some numbers when they add together equal to the sum of other numbers add together. And these two groups don't have repeated numbers. These two groups don't have overlapped numbers. See? Yeah. Okay, so this is application. Okay, now we are going to prove more complicated questions, and I think this could be this could consume all the time of these lectures. Yeah, and let's try to first understand the questions. So increasing sequence. This example. So maybe like Emma Shi, can you help us read the questions? So just read the questions here. Read this whole question. Yeah. Oh, Emma Shi.
Like question 2,
Yeah. Yeah. Read.
increasing, decreasing sequences.
Yeah.
This example has to do with permutations. A permutation of n is an ordering of the numbers from 1 to n. For example, a permutation of 7 is 1, 4, 3, 7, 2, 6, 5.
Okay, so I'll stop you here. So can you explain in your own word, like what is a permutation? So what is a permutation of 7?
Like the numbers 1 to 7.
Yeah. So the number 1 to 7. So what make it a permutation?
Because it's an ordering of the numbers 1 to 7.
Yeah, exactly. So a permutation means you permute, right? So it means like you change the ordering. So the natural ordering from 1 to 7 is 1, 2, 3, 4, 5, 6, 7, right? A permutation is that you reorder them, right? Reorder them in some random way. So it's like you shuffle them, right? If you bought a deck of cards, it is like ordered in increasing order 1, 2, 3, 4, 5, 6, 7, right? And if you shuffle the card, you reorder the card, then it is called a permutation. It can appear in any orders. So 1, 4, 3, 7, 2, 6, 5 is a permutation. Maybe Jason, can you give another example, another permutation of 7? I mean, there are tons of permutation of 7.
1, 2, 3, 4, 5, 6, 7.
Yeah, that is a valid permutation. So you can not change it at all. Maybe Mark, can you give another example?
1, 2, 4, 5, 6, 4. I don't know, 7. Just a random order.
Yeah, a random order. Okay, let's stop here. So I think you all get the idea of what is a permutation. Yeah. So then I will give you another question. So before we dive deep into this questions, this question is very complicated, right? You see there are some funny symbol here. I really want you to understand the permutation. So let's actually count how many permutations are there, right? So a permutation of 7. So let's only think of the number of permutation of 7, right? It can either be 1, 2, 3, 4, 5, 6, 7, or 7, 6, 5, 4, 3, 2, 1, or it's like a 1, 4, 3, 7, 2, 6, 5, like random order, right? Now how many different permutations are there? So let's think about this problem for maybe 3 minutes, and I would ask you to answer these questions. So you see, it's another counting problems, right? So if you don't know the answer or don't know how to approach it, I really hope you to rethink about how we count the number of subset, right? We use some clever ways, right? We use 2 times 2 times 2 times 2. It is called the multiplication method. So it's a lot of numbers multiplying together, right? That is a classic way to count something. So maybe we can use the multiplication method here. So I want each of you to think how to count the number of different permutations of 7. Yeah, I will mute myself for 2 minutes and let you think on this problem. Okay, maybe I'm not sure. Do you know an answer or a guess? Like how many number of permutation of 7? Different permutation of 7?
Uh, maybe like for example, because there are like 7 numbers, but like they have to be arranged differently.
Yeah.
So like the first number, like you can pick 1 to 7, which is like 7 numbers, but like when you pick the second number, you can only pick 6 numbers because you already picked one number.
Exactly. Yeah.
So it should be like 7 times 6 times 5 times 4 times 3 times 2 times 1.
Yeah, very good. That actually has the name. It's called 7 factorial. So by 7 factorial, it means 7 times 6 times 5 times 5 times 4 times 3 times 2 times 1. Yeah, like 10 factorial is 10 times 9 times 8 times dot 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 times 1. Yeah, cool. And that's a really good answer, and you actually explain it. Yeah. So now I think all of you have a good understanding of what a permutation is, and let's actually read the theorem. So I mean every permutation of n, right? Every permutation of n either has an increasing subsequence or a decreasing subsequence of length. This. So means square root of n, right? Square root of n. But also this is called the ceiling of square root of n. So I know most of you may have a question on what is a ceiling, right? So maybe Jason, can you help us read this paragraph, which explains perfectly what is a ceiling?
Here, ceiling pronounced ceiling means to round up to the next integer. For a permutation of 7, the theorem guarantees an increasing or decreasing sequence of length at least ceiling root 7 equals 3. For example, in the above, 147 and 126 are both increasing subsequences of length 3, and 432 is a decreasing subsequence of length 3.
Cool. So you see 7, right? Root 7 is like 2 point something. So ceiling means round up, right? Round up to the next integer. So if it's even if it's 2.1, you round it up, it becomes 3. If it's 3.1 or even 3.01, you round up, it becomes 4. So ceiling means always round up, right? And like floor, so there's another symbol called floor. Floor means rounding down to the next integer. So ceiling means rounding up, right? So it means that you will have an increasing subsequence or decreasing subsequence, and the length is approximately root n, right? But the root n is not an integer. The length is of course an integer, right? So you round the root n up to the next integer, which is called ceiling for root n. Okay, so now I think all of you may have another question. So what is a subsequence, right? What is a subsequence and what is an increasing subsequence? So subsequence meaning, for example, 1, 4, 3, 7, 2, 6, 5. This is called a sequence, right? Because it's a sequence of number. It's an array, it's a sequence of number. Subsequence meaning you keep the original order, but you can jump. You see, 1, 3, 6, 1, 3, 2 are all valid subsequence. Subsequence is that so you cannot be like a 3, 1, 2 because 3, 1, 2 is not it's not consistent with our order. So as long as it's consistent with our order, you can jump for jump 3, right? So 1, 7 and jump 2, jump 6, 5. 1, 7, 5 is another subsequence. So subsequence is jump, but it's not an increasing subsequence because of 1, 7, 5. So 7 is greater than 1, but 5 is not greater than 7, so it's not increasing. By increasing subsequence, it means that you jump to some numbers, right? But in each jump, you jump to a higher number. Say 1 jump to 3, 3 jump to 7, and we omit all the other numbers. So 1, 3, 7 is a subsequence, and it's also increasing, right? Maybe like Mark, Mark, can you give us another example of an increasing subsequence? So I just gave 1, 3, 7.
Like 4, 5, 6, 4, 5, 6.
But 4, 5, 6 is not a subsequence. Why? You are not consistent with the order, right? Because 4 then is 6 then 5, right? You cannot change the order of 6 and 5. Yeah. So it's not a subsequence. So Mark, can you give another increasing subsequence? Because you cannot give 4, 6, 5. Or you cannot give 4, 5, 6. The only subsequence out there is 4, 6, 5. But it's not increasing.
1, 2, 5.
1, 2, 5. Yeah, that's valid. So 1, 2, 5. Yeah, you keep the original order, and so it's a subsequence, and it's also increasing. Cool. Maybe Amayu, can you give another increasing subsequence?
Did you say 137 yet?
Yeah, maybe give us something.
Oh,
Yeah.
146?
146. Yeah, that's also valid. Cool. So maybe Hector, can you give us a decreasing subsequence? So decreasing subsequence is also like increasing subsequence. First, it needs to be a subsequence. It needs to keep the original order, but the number you select must be decreasing. Yeah. So what can be a decreasing subsequence?
765.
Yeah, 765. Very good. Yeah. You see, so 765 is a decreasing subsequence. And of course, 75 or 76 is also a decreasing subsequence. It's just not long enough. So the problem is trying to prove that there exists an increasing subsequence of length like more than root n, right? So it's trying to prove that out of any subsequence, out of any permutation. So you can reorder it to something really like ugly or really like really random. But no matter how you permute it, no matter how you like shuffle it, there will always exist a subsequence, increasing subsequence that is long enough. That is very long, right? That is longer even than root 10. That is quite interesting, right? Quite interesting. So we all know that. So let's also get another example to help us be more familiar. So we all know that like root 9, right? Like root 9, right? So I say root 9 is what? Root 9 is also 3, right? So let's actually say root 10, right? Root 10 is a 3 point something, right? It's greater than 3. So ceiling of root 10. So maybe Jason, do you know what is a ceiling of root 10?
I think 4.
Yeah, 4, because it's greater than 3, right? And you round up, so it's 4. Cool. So let's get let me write some random permutation. Or yeah, let's write some stuff like yeah. Oh, and I forgot 2, and 2 maybe here. Yeah. So it means it has a subsequence that's increasing or decreasing, and it has a length of 4, right? So that is quite long. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So this is a valid permutation. And maybe I'm not sure. Can you give us maybe increasing subsequence that is of length 4?
Uh,
An increasing subsequence. Yeah.
4.
Of length 4. So you need to give 4 numbers, right? At least 4 numbers.
1, 2, 3, 4.
1, 2, what 4?
3, 4.
But 3 is before 1, right? So if you 1, 2, you already go to here, you cannot go back to 3, right? Because it's a subsequence, it must be the same order as this permutation, right? So you cannot be 1, 2, 3, 4. You cannot go back, right? You can only be 3, 1, 2, 4, but then that is not an increasing.
Maybe 4, 5. No.
I mean, of course, you can start
2,
with
4, 5, 8.
yeah, 2, 4, 5, 8 is valid. And I mean, you can of course start with 1, right? 1 is here, 2 is here, 4 is here. You can even go to 5 and 6, right? 1, 2, 4, 5, 6 is actually last 5, right? So it's actually longer than 4. But that doesn't matter. So our theorem here only guarantees that you have an increasing subsequence or decreasing subsequence at least last 4, right? I mean, if you have a last 5, that's great, right? I mean, last 5, then you can cut one number and it's still last 4. Yeah. Okay. So yeah, so maybe if we permute it a bit to make it more complicated, this is like 1, 2, 4. You see, in this you cannot find a increasing subsequence of length 5, right? So 1, 2. So 1, 2, and then you can either 4 and 8. 1, 2, 4, 8 is the length 4, right? 1, 2, and 1, 2, 4, you can also go to 7 or 6. So 1, 2, 4, 6, the length is also 4, right? It cannot be 5. Yeah. So I mean, so maybe your permutation is good, right? Maybe your permutation is like this, right? 1, 2, 3, 4, 5, 6, 7, until 8, until 10, right? If you're lucky enough, you have of course increasing subsequence of last 10. It's just all the numbers, right? Because 1, 2, 3, 4, 5, 6, 7, 8, 10, 8, 9, 10. Here is a subsequence of this permutation, right? They have the same order. But if your permutation is random enough, it may be hard to find a very long increase in subsequence. But our theorem guarantee that it has at least a length 4 increasing or decreasing subsequence. So that's quite magic, right? And that can be solved or proved by pigeonhole principles. Okay, so let's read the proof directly. The proof is quite clever. It first use something, it first creates something, and maybe Jason, can you read this paragraph So just read the words here. Yeah.
Proof. We will associate to every number in the permutation an ordered pair of two integers. The first integer associated with a number k will be the length of the longest increasing subsequence ending with k, and the second will be the length of the longest decreasing subsequence ending with k. Thus, for the subsequence above, the ordered pairs will be
Okay. So let me take an example. So for each number like 1, 4, 7, 6, 2. So let's use this permutation as an example. So each number is like 1, 4, 7, 3, 7, 2, 6, 5, right? For each number. And you got a pair, right? You see this is a pair, this is a pair, this is a pair. And for each pair, the first number in the pair is the longest, right? It's the length of the longest increasing subsequence ending with k, or in this case, ending with 1. Because 1 is already the first number. And if you end with 1, you can only be 1, right? So the length of the longest increasing subsequence is of course 1, right? 1 itself is a subsequence, and it's of course increasing because it only contains one number. And 1 itself is also a subsequence, and it is of course decreasing because it's only one number. So one number sequence or a length 1 sequence is of course both increasing and decreasing. Yeah, so the length of the longest is 1. The length of the longest decreasing is also 1, right? Because you end with 1. You cannot go further. You end, right? And ending with 4, the length of increasing subsequence is of course 1, 4, right? 1, 4 is increasing. But the length of decreasing subsequence and with 4 is of course 4, right? For itself. And the length is 1, right? Because 1, 4 is increasing, 1, 4 is not decreasing. And in order to be decreasing, you can only be 4, right? The number 4 is itself is a subsequence. And this subsequence is of course decreasing because it only contains one number. Yeah. So that's it. So then the length of the longest length, right? The length of the longest increasing is 2, which is 1, 4. The increasing subsequence ending with 4, right? So maybe Amayu, can you help us explain why corresponding to number 3 is 2, 2? Yeah. Still this permutation. So what does this 2 mean?
What? It's decreasing? I don't know.
No, this is the first number of the pair, right? So what does the first number of the pair correspond to? It corresponds to the length of the longest increasing subsequence ending with the k, and k here is 3, right? So can you tell me what is the longest increasing subsequence ending with 3? What is the length of the longest increasing subsequence ending with 3?
4. I don't know. I'm so confused.
Let's break it down. So ending with 3, what can be a subsequence ending with 3? So it means stop at 3. A subsequence.
How long? Like,
You can be 1, 3, right? 1, 3 is a subsequence, right? 4, 3 is also a subsequence, right? 1, 4, 3, 1, 4, 3 is also a subsequence, right? But 1, 4, 3 is neither increasing or decreasing, right? Yeah. So in order to be increasing, you can only be 1, 3, right? I mean, of course, you can also be 3, right? 3 itself is also a subsequence, and it's of course increasing, right? I mean 3 itself. Do you agree on this? I mean a sequence can be of length 1. I mean 3 itself is an array, right? If I say a list can of course contain only one number, right? I mean a list of student can of course be like only one student. One student form a list, two students can form a list, three students can form a list, right? So 3 itself can be a subsequence, but the length is only 1. And 3 itself must be increasing, right? And it's also decreasing because there's no next number to compare with. Do you get this? Yeah, so 3 itself is an increasing subsequence, and it's also a decreasing subsequence, and it's also anyway 3, but it's not the longest one, right? Because we have 1, 3. 1, 3 is also a subsequence, Do you get this?
Mm-hmm.
Yeah, 1 3 is an increasing subsequence, and it's of course the longest one, right? Because you can have a longer one. 1 4 3 is a longer subsequence ending with 3, but it's no longer increasing. So 1 3 is the longest increasing subsequence ending with 3, and what is its length is 2, right? And can you give me a longest decreasing subsequence ending with 3?
Oh,
Yeah,
7, 6, 5. No, wait.
ending with 3.
No.
You
Wait, 4,
cannot
3,
go.
4, 4, 3, 4, 4, 3, 3.
Yeah, 4 3 is a valid example, right? Because ending with 3 means you cannot go past 3, right? So you just ignore all the numbers after 3. It can be 4 3, right? 4 3 is a subsequence. 3 itself is also a subsequence, and they are all decreasing. And what is the longest one? So 4 3 is the longest one, right? And the length is what?
Mm-hmm.
The length is 2, right? So you write 2 as a second,
Mm-hmm.
as a second number of the pair. Okay, cool. I think now you fully understand. And now let let Hector, can you explain explain
Uh,
the 7? Yeah.
oh, okay. So for increasing subsequence, it's 137 or 147. The largest is length is 3, and for decrease subsequence is only 7, so the length is 1.
Yeah, yeah. So for the 7, it can be 137 or 147. The length is 3, right? And for 7 itself is 1. Okay. So I think now all of you get what it means, right? Like for example, for 6, the increasing one can be 136 or 126 or even 146, right? So the length is 3. And for decreasing one, it can only be 7 6, right? Because 6 is quite large. To decrease, you can only be 7 6. And of course, 6 itself. But 7 6 is longer and its length is 2, right? Cool. And for 5, it can be 7 6 5, which is length 3, right? And for increasing one, it can be 1 2 5, 1 4 5, or even 3 6 5, and the length is also 3, right? Okay, so now you understand this. So, okay, cool. And another claim. So this claim I will leave as I will give I will leave as like homework, and today we'll end a bit earlier, and so for the rest of time you can so I already sent this PDF to the group, and you can try to use the remaining time to try to understand the claim. I mean, the claim itself would not prove the theorem directly, but it is a like a exercise. I encourage you to think a bit. So why all these order pair are distinct? You see, 1 1 2 1 2 2. Maybe they have the same first number, or maybe they have the same second number, but you see, neither have the same, both the same first number and the same second number, right? So all the order pairs are distinct. You do not need to think about the case where there are like n numbers. Just think of this specific cases, right? This permutation, and think why all order pairs, like all these pairs, are distinct, are different, right? Why is them all different? So why can't we say end with 3 and end with 7? We both have the same length of the longest increasing subsequence and the same length of longest decreasing subsequence, right? Why can't that happen? I encourage you to think about this for 5 minutes and then go through this proof. Yeah. So this is like this is actually an explanation or intuition of the proof and following it, right? A proof of claim. This is the like a more mathematical form of the proof. Yeah. So in the next lecture, we will go back and to teach the proof of the claim. And if some of you already understand the proof, you can like be brave and raise your hand and explain the idea of the proof to the whole class. Yeah, and I encourage you to do this. And after that, we'll go through in the next lectures. We'll go through some more complicated and more funny games of pigeonhole principles. And after next lectures, I will give you a set of actual practice of pigeonhole principles, and those will be real math questions from important math competition. I know some of you may take AMC or AIME, so those questions are directly from AMC or AIME or from Ross. Ross is a well-known math camp, so maybe some questions from Ross are entirely so the entire questions are about pigeonhole principles. So this is a really important principles, and I encourage you to study it like in deep level. Yeah. So let's end this lecture a bit earlier today since I need to get to the airport. Yeah. Okay. Thank you.